welcome back. We are going to go into the last bits of chapter 2 to finish up second order differential equations. So as usual, give you guys around 1.5 to 2 minutes to look at those three. I just a little bit from the ones I put up last time. But yeah, feel free to discuss it with your neighbors as well, with your friends. If you don't have friends, feel free to make some. And you don't have to work out the whole thing as usual. Just sort out if you guys agree on what's the right method to go about it. Some of them are homogeneous, some of them are non-homogeneous. Anyway, go ahead. I'll catch up with you in a minute and a half. I'll sort of the plan today is to go through mainly those three techniques. Those basically encompasses, I put some homogeneous, some of them homogeneous, some of them inhomogeneous, a mixture with different things. So that's what the kind of thing you will expect to see in an exam, right? You've learned sort of the homogeneous parts, how to deal with the homogeneous part and inhomogeneous parts separately a little bit. But in an exam, usually in one question, they'll just test you everything like that. Okay, so so that's the plan. So picking up from last time, just a quick summary of the lot of sub-chapters in chapter 2. And let me just break it down for you so it's easy when you're studying and revision, you know what to focus on. Chapter 2.1 to 2.5 is basically just a bunch of knowledge, just picking up from where we ended last time. Right, so chapter 1 is an intro, chapter 2 is a bunch of definitions, things that you need to know, not necessarily introduce a new method, those come later. Chapter 2.3, if I remember what that is, examples, so some examples, and then introducing the concept of initial conditions and boundary conditions, and the idea of linearity of solutions. So the fact that you can add up two solutions to form a general solution for homogeneous ordinary differential equations, that is an important property. So these are sort of knowledge that you need to know, and then really the subchapter here summarizes the main methods that I introduced, and as we sort of did at the end of last time, there's constant coefficient types, and there is the Euler type. Euler equations. There are lots of equations in math called Euler equations, by the way. Just be careful. This is one of them. It's of second, mainly specifically referring to second order ODEs. There's the Euler type. And then there is the method of reduction of order. And then there is finding standard particular integrals. And probably the most difficult one, right? The variation of parameter, the one with the Wronskian variation of parameter. Okay, so I guess in 2.10 there's also a mention of coupled ODEs. So we've seen a little bit of that at the end of chapter 1 with eigenvalues, but that was first order, so this is applying it to second order. Like that. So these are sort of the main methods. Again, let me group it to you. These are the main two forms. So the main forms you will need to recognize. Okay? And this is a technique where if you know one solution, again, I think everyone is familiar that if you have a second order ODE, you expect two independent, linear independent solutions. So if you know one of them, the reduction of order methods basically is a nice recipe to find the second one. And then here are the ways to deal with if your ODE is not homogeneous. So if you have something on the right, for example, like example 1 and 2, you have something on the right-hand side, then you use one of these methods. This is if something is easy to identify. I think the problem 1 is something on the right-hand side is simple enough. You can almost directly make a guess solution and go with it. And then if you have something number 2 that's more complicated, you have sort of the general method that solves everything, the variation parameter. This is, probably won't get to it, and it's sort of just an extension. If you understand chapter 1 with eigenvalues, it's basically if you have a coupled system, it's the same procedure. Right, there's a matrix, and now you have You have a derivative, you have a matrix that is not diagonal, so you diagonalize it, and then now it becomes a ODE, a second order ODE. Usually in an exam, because of all that work, we won't combine it with something very difficult. After you diagonalize it, usually it becomes constant coefficient. Once it becomes constant coefficient, you can just use the simple method to solve it and then change it back to the original coordinates. Okay? So it's nothing too too difficult. We've done enough examples of that. With first order, it's just the second order version of that. Okay? Yeah, so this is to deal with inhomogeneous ODEs. Okay?